this next example, we start with a 1.11 microcoulomb charge and a negative 2.22 microcoulomb charge. They're held at rest and they're separated by a distance of 10 millimeters. Let's go ahead and draw that as we get started. So here's our first charge. I'm going to call this Q1 equals 1.11 microcoulombs. It is 10 millimeters. I'm going to draw it 10 millimeters horizontally. From a second charge, which is negative, I'm going to call that one Q2, and that's minus 2.22 microcoulombs. Part A, find the electric potential energy of this configuration of charge. Okay, this is what we did in the previous parts. We say our electric potential energy is K times Q1 times Q2 divided by the distance between them. We can just put our numbers in here. 8.99 times 10 to the 9 Newton meters squared over coulombs squared times 1.11 times 10 to the minus 6 coulombs times minus 2.22 times 10 to the minus 6 coulombs divided by 10 millimeters. Got to put that in meters. So 10 times 10 to the minus 3 meters. Put all this in the calculator, and what we get for that energy is negative 2.2153 joules. Okay, so that's the initial potential energy. The next thing we do is we take a negative 3.33 microcoulomb charge and we put it 10 millimeters from the original two charges. So we're making an equilateral triangle here. So we're putting in a new charge, negative, and it's 10 millimeters away this way, and it's 10 millimeters away this way. And this one is Q3 equals minus 3.33 microcoulombs. Part B. Find the electric potential energy of this new configuration of charge. Okay, here we have to figure out what does it mean. Well, we know that we have potential energy when we have an interaction. So there's a potential energy between 1 and 3. There's a potential energy between 2 and 3. And there's a potential energy between 1 and 2. To get the total potential energy, we have to add up all of the possible interactions. So when we have multiple charges, we find our total electric potential energy by doing the sum of all of the individual combinations. So we might write it that way in math speak. So our total electric potential energy is going to be the potential energy between 1 and 2. We've already got that bit done. Plus the potential energy between 1 and 3. Plus the potential energy between 2 and 3. Potential energy between 1 and 2, minus 2.2153 joules. So we just did that in part A. Potential energy between 1 and 3 is K times Q1 times Q3 divided by the distance between them. That's our 10 millimeters. Put that in the calculator. We should get minus 3.3230 joules. And between our last combination is 2 and 3, K times Q2 times Q3 divided by the distance, again 10 millimeters, equals plus 6.6456 joules. And then our total potential energy is the sum of all of those numbers, 1.1076 joules. Okay, part B done. There's our electric potential energy when we have these charges held together like this. All right, next, part C. We release our 3.33 microcoulomb charge. We release Q3, and it's allowed to move. How does it move? What's the work done while it's moving? And think about the sign of the work. So those are all important things to figure out. Why don't we take a new sheet of paper and just quickly resketch those charges. So I've got my Q1, that's positive. I've got my Q2, that's negative. And I've got my Q3, that's negative down here. And then if we want to remember the relative magnitudes, that's kind of 1.11, 2.22, and 3.33. So what happens to the motion? Well, Q3 is going to be attracted to Q1. There's going to be a force there. And it's going to be repelled by Q2. Q2 is bigger than Q1, so it's going to be repelled by a bigger force. So there's my force between 1 and 3. There's my force between 2 and 3. If I wanted to do the net force, I would do a vector sum of those two things, so I would figure out my components, and my net resultant would look something like this. F net. Point to the left because they both point left, ultimately point down because this one points more down than this one points up. So what's going to happen to Q3 is it's going to move away from Q1 and Q2. So let's talk about that. Let's write that down first. Q3 will move away from Q1 and Q2. So that's our first result. Find the work done by the electric field. Well, the work done by the electric field is negative of the change in potential energy minus U final subtract U initial. Our U initial, well, we just figured that part out. U initial equals 1.1076 joules. U final, that's pretty interesting. This is going to stop moving. Our final situation is going to be when this Q3 is very far away. So U final means when Q3 is far away. If Q3 is far away, that means the potential energy between 1 and 3 is about 0, and the potential energy between 2 and 3 is about 0, and the only potential energy we'll have left is the potential energy between 1 and 2, which was minus 2.2153 joules. So now finding my work equals minus my change in potential energy. That would be minus negative 2.2153 joules, subtract 1.1076 joules equals plus 3.3229 joules. So my work done is positive. Let's think about what does it mean that our work done is positive. Well, our force is this way, and the displacement was also this way because it's being pushed away. So my work is positive, and it's positive because my force and displacement are in the same direction. Okay, there's one little bit more to this problem. Part D was find the speed of this charge when it's very far away. Okay, so we said our final case, Q3 gets very far away. Let's see how fast it's going. And we'll just grab another sheet of paper. So let's think about our initial and our final cases. So initially, we had our plus here and our negative here and our negative here. And in our final case, still got my plus and my minus, but my Q3 is gone very far away. Far away. So if we want to see how far it's going, maybe we'll put a box around them just to make sure we recognize that those are two different steps of the problem. Let's apply our conservation of energy. Again, we couldn't use kinematics here because the force is changing, so the acceleration is always changing. E final equals E initial plus work done by non-conservative forces. That bit's going to be 0 because there's no friction. E final equals E initial. K final plus U E final equals K initial plus U E initial. K final is 1/2 times m times V final squared. That V is what we're trying to find. Our final potential energy, we already calculated that one. K initial, well, we've released everything from rest. Charges at rest. So initially nothing was moving, so our initial kinetic energy is 0. And our initial potential energy is also something we knew. All right, so 1/2 times m times Vf squared is equal to 1.1076 joules. Subtract a negative 2.2153 joules to give us 3.3229 joules. We'd like to solve for our Vf. Vf is going to be 2 times this value divided by the mass, and our mass was given as 3 milligrams, which is 3 times 10 to the minus 6 kilograms. A milligram is a thousandth of a gram, which is a thousandth of a kilogram. Don't forget to take your square root, and we get a final speed of 1488 meters per second. So it's actually going pretty fast after it gets far away.